it's kind of a fun little problem. We're trying to figure out the area of this triangle and we're given the location of the 3 vertices. There's at least 2 different ways you can solve it. I think the most efficient, which I didn't think to do, is a linear algebra method where we use one interpretation of the cross product. More on that later, because that's not what I thought to do. What immediately came to mind for me was, well, let's see, I know the locations of the vertices, so I know the distances between the vertices, I know the lengths of the 3 sides of the triangle, I can get the area really easily using Heron's formula. In case you're not familiar with that, Heron's formula just tells you that if you have this triangle ABC, whose side lengths are little a, little b, and little c respectively, the area of the triangle is just equal to the square root of s times s minus a times s minus b times s minus c, where s is equal to the semi-perimeter, in other words, halfway around the perimeter, in other words, a plus b plus c divided by 2. I got my roadmap, I plug in some numbers, and I'm done. To figure out a, I need to know the distance between vertices b and c. Vertex b has components 3, 1, and 2. Vertex C, as I learned the hard way, has components -2, 0, and 4. I went through and I solved the problem with 2, 0, 4. It works out really nicely, but it doesn't produce any of these answers. Hopefully your test prints better than this PDF did. Anyways, the distance formula in 3 dimensions is almost identical to the distance formula in 2 dimensions. You just need the square root of the sum of the squares of the differences in each of the dimensions. What I'm saying is 3 minus -2 is 5, 1 minus 0 is 1, and 2 minus 4, it's -2, but I'm just going to write 2 because I'm going to square these numbers over here, so negatives will go away. Length A is just the square root of 5 squared plus 1 squared plus 2 squared. In other words, 25 plus 1 plus 4, in other words, 30. Oh, that's unfortunate. I was really hoping the test makers were going to pick these numbers carefully so that this would be an integer value, so that I can calculate things like the semi-perimeter in this area without the help of a calculator. At this point, a less stubborn person might give up on this method and think about a more clever way of solving this, but I didn't. I kept going. We can figure out side length B in much the same way. It's the distance between vertices A and C. The components of vertex A are 1, 3, and 2. In case you haven't figured this out by now, I'm calling this A, this B, and this C. The components of vertex C, as I wrote right here, are -2, 0, and 4. The difference in these components is 3, difference in these is 3, difference in these is 2. 3 squared plus 3 squared plus 2 squared is what, 9 plus 9 plus 4? 18 plus 4 sounds like 22. Pushing on, I figure out side length C by finding the distance between vertices A and B. A still has components 1, 3, and 2. B has components 3, 1, and 2. The difference here is 2. Difference here is 2. Difference here is 0. So I get 2 squared plus 2 squared. Length C is just the square root of 8. No easy way to add up these 3 numbers to calculate the semi-perimeter. Could you leave S as an expression in terms of these 3 guys, and then subtract each of them individually, and then factor and multiply really cleverly to get the answer? I don't know, maybe. Sounds like a lot of work. What would be a lot cooler is if you stared at these 3 numbers and recognized a relationship between them. Maybe you'd be able to recognize that 8 plus 22 equals 30. What I'm saying is this squared plus this squared equals this squared. In other words, the sum of the squares of 2 lengths of this triangle is equal to the square of the length of the third. If that sounds familiar to you, that's awesome. That's what's called Pythagorean's theorem. The square root of 8 squared plus the square root of 22 squared is equal to the square root of 30 squared. Therefore, ABC is a right triangle. And since square root of 30 is the largest of these 3 lengths, this must be the length of the hypotenuse. I guess I can't be too mad at the test makers for not choosing these to be integers, because they did choose these to at least give me a right triangle, which is really nice. Let's see, side length A is root 30, therefore this is vertex A. Maybe I'll throw vertex B over here, in which case this leg has length root 22. Vertex C up here means that this leg has length root 8. As I'm sure you're aware, the area of a triangle is just half the length of the base times the height. So in this case, it's 1/2 root 8 times root 22. Let's see, root 8 is 2 root 2. So 1/2 times 2 root 2 is just root 2. Root 2 times root 22 is root 44. In other words, root 4 times root 11. In other words, 2 times root 11. The answer to this question is A. You might argue that I got a little bit lucky here, right? In addition to not making the side lengths integers, the test makers could have also not made this a right triangle, and that would have made this method of solving completely moot. I mean, I still could try to use Heron's formula, but I suspect it'd be a mess. To tell you the truth, I'm a little curious now. I wonder if you could plug these in and do lots of expansion and reasonably get the answer. But whatever, I'm not going down that road. What I'm going to do instead is talk about how you could solve this by figuring out the cross product. So why the cross product? Well, one interpretation of the cross product is that the magnitude of the cross product gives you the area of the parallelogram that's kind of defined by the two vectors in the cross product. So if this is u and this is v, the magnitude of u cross v gives me the area of this parallelogram. Why is that relevant? Well, think about A living down here and B living over here and C living up here maybe. If I want the area of this triangle, all I got to do is figure out half the area of this parallelogram. What I'm saying is the answer to this question is going to be half of the magnitude of the cross product between any two of these vectors. So let's calculate some vectors. Let's see, vector BC, as I kind of figured out down here, has components 5, 1, and -2. Now all of a sudden the negative signs matter. Maybe I should have been a little bit more careful earlier. What about vector AC? Here the components are 3, 3, and -2. And while I don't need it, I'm going to check my answer by figuring out the components of vector AB, which as I figured out down here would be -2, 2, and 0. To figure out the cross product of these two guys, one way to do it is to write one of the vectors, and then right below it, write the other vector, 3, 3, and -2. And then write I, J, K up top, and almost think about like taking the determinant of this 3 by 3 matrix. All right, so I'd first focus on I, and I'd multiply that by the determinant of the 2 by 2 matrix that I'd see if I ignored this column in this row. So 1, 3, -2, and -2. And then from that, I would subtract J times the determinant of the matrix that I'd get ignoring this column and row. So 5, 3, -2, -2. And then I didn't plan this out well, but fine. After that, I would add K times the determinant of the matrix that I'd get ignoring the first row and the third column. So 5, 3, 1, 3. But instead of summing these three things, these are going to be the three components of a vector. So BC cross AC would have an I component of -2 minus -6. In other words, -2 plus 6. In other words, 4. The J component would be the negative of -10 minus -6. So -10 plus 6. So -4, -4, sounds like a 4. And then the third component I'd get by considering the determinant of this matrix, 15 minus 3, gives me a 12. To figure out the magnitude of this cross product, I need the square root of the sum of the squares of the components. So 4 squared plus 4 squared plus 12 squared. Those numbers will get a little bit big. If you want to show off your arithmetic skills, go right ahead. But I think what I would do is say that 12 squared is 3 squared times 4 squared. So 9 times 4 squared. So I got one of these 4 squareds here, another 4 squared here, and 9 of these 4 squareds here. So I got 11 of these 4 squared things. So I got the square root of 11 times the square root of 4 squared. I got 4 root 11. Come down here, look for 4 root 11. You put in your answer as E and you're super disappointed. Why? Because the cross product does not tell me the area of this triangle. It tells me the area of this parallelogram, and this parallelogram is made up of 2 of these triangles. Half of the area of the parallelogram, half of 4 root 11, gives me the 2 root 11 that I was looking for. I'm pretty low on room, so I don't think I'm going to check my answer, but if you wanted to check your answer, you could take 2 different vectors, maybe these 2 right here, and calculate half the magnitude of their cross product, and you should come up with the same 2 root 11.